and this is my assignment 5 walkthrough. I'm going to try not to make it too awful long, but it didn't look like there was a requirement on length. So I did want to go through all of the expected outcomes and show you how they work on my system. Okay, let's go ahead and just get started. So I've got it set up where it's really easy. You can just literally hit run leader. That runs the server for the distributed network, and then I've got it where you can run client. You actually don't have to run the client or the nodes in any particular order. You just have to have the nodes up and running before you submit anything from the client. But you can see on my server that it has a client thread running. I ran it to where it scales upwards. You can actually have multiple clients on this thing, but I didn't. But I set it up for like a later implementation. But I did set it up to where it will keep accepting clients. But for my implementation, I would just I would just leave it at one client if at all possible. But I do expect to go back later when this class is over and play with it and try to get multiple clients running. Specifically with this one, keep it with the one client just because we're only you've only allowed 3 to 5 nodes, and I don't want to. And then I have set it up to where I could scale the nodes upwards, which would make it easier for me. But anyway, I've got run. You can't see it very well, but this is run good node. That means the node is going to perform as expected. Let's go ahead. I'm going to show you with a bad node for this first one, and with another good node. Okay, cool. You can see I've tried to make it pretty friendly. There's a handshake request between the client and the server, just because. They also run on different. They run on different ports, so they all are on localhost right now. I could implement that to change that, but just for grading purposes and making it easier, I left it at just a local host, and then they have different ports. So you can see right here, the port 800 is where the clients are coming, and then 900 is where the server is accepting node connections. I'm assuming that security would be fine with that because, I mean, but I could also implement a handshake later on if I was really worried that my nodes were not really nodes. But I didn't do a handshake with the nodes just because I assumed that those would be all up and running and nobody would know about my specific port. But you could still do a handshake. But with the client, I did do a handshake. So it sends over a handshake, and then if the client program understands my JSON structure and my protocol, then it sends back, and then you can see where the client receives, the client gets the protocol handshake, and then it says the request on the client side was successful and it welcomes the client, and then asks to provide a list of numbers. You can also see where the nodes are running, and these are running threaded, and I could put it, I set the limit to where it would only allow up to 5 nodes, but we can, but they're all threaded, and you'll see how that goes. Okay, so let's put in a example. 5, 6, 7, 8, 9. Okay, so just looking over here, the commands to run in your program. Oh, sorry. So the client accepts a list of numbers, delay value, and then sends it to the leader for processing. So here is the list of numbers. And now it's going to ask for delay value. Let's just say 100 to keep it simple. You can see where the delay value was the data transmitted and where it received. On my node side, you can see where it received the quiet request. Here's the values there. And then you can see where the thread is running with the sub list 1, 2, 3. Another thread is running with 5, 6, 7. They're threaded, so some of them are not coming in like particular order. It sends the node request for that 1, 2, 3. It runs the thread for 7, 8, 9. It sends the request for 7, 8, 9. And then it sends the request for 5 or 4, 5, 6. You can see where it received the responses. And these are nodes right here. I didn't put a terminal for those. because it was all over here, and I mean, I could, I guess, if you really want me to, um, but I didn't think it was necessary. And then this is where the nodes completed the tasks. I used an executor servicer. So and then what the really cool thing with that is I learned that it gives you a future object. And so I collected all the future objects for these tasks, and then I created a wait, essentially a get. It says it's .get, but it's a wait essentially that waits for all the threads to complete their task. And then they put all and then it returns with the future. It can return it returns like a Boolean value, and essentially, so that's how it tells if they are correct, or if they are correct or not. But so this one right here, all the tasks complete, but you can also see where it has the processing time elapsed and the single sum for the single so mine actually runs faster, it looks like, when it's distributed for this one. And then it does a checksum. So it reruns those lists with different, it takes essentially just moves them over and reruns. So it sends it, and then the node requests, or sorry, it spins up a thread essentially, and then it sends a request in my JSON to my node server. Then they run with the sum that they had gotten before, and then when they come back, they I didn't put this, I should, but they essentially return that boolean because it's callable for the future, and then it returns a boolean value, and that boolean value dictates if it agreed or not. And then as you can see, the success was fail. The type was the request that it sent, and the message was it was a checksum failure. So we have a node on here that didn't work, and it didn't agree when they switched it over. I also had where you can continue on, so it runs in a little loop. You can continue sending other things. But let's go ahead and drop these real quick. Oh, I forgot. I could also hit quit, type quit, and it will gracefully run my program off. But let's just do it quick and dirty here. And then, okay, so let's rerun these again. So let's run our leader. Oh, did I? Gradle run leader. There we go. I don't know what I did wrong. I must have hit something wrong. Okay, and so we see our server started. Connect on clients. Let's run our client, and then run good node. And let's run all good nodes so that I can walk you through these and you can see what's going on. Run good. Oh, sorry. Run good node. Awesome sauce. And run good node. Okay, cool. So now we have a distributed network with all the good nodes running. So let's do that again, where you can see the example of a distributed sum coming back. So we go ahead and send that and our delay. Perfection. We got all of our responses back. Everybody did its checksum, and you can see over here the response was true. The sum was 45, the request, and then I printed out really nicely. So computation successful. 45 is the sum. Distributed times, looks right here, or non-distributed times was a lot longer than our distributed times, and we can submit another one. So you can see over here, that is that distributed thing. Going through the points real quick. Obviously our client accepts a list of members and delay value. Our leader divides the tasks up into smaller portions and sends them out. It also does a checksum and performs a simple consensus. The nodes each calculate the sum of the portion of the list, simulating a long computation time. I'll go in and actually do a print ln so you can actually see the nodes running, because I think that might just be important just for grading purposes, and just so you can see that they're actually doing something. And then the leader can be started via Gradle task. As obviously you see, the client started via Gradle task, and the nodes are started via Gradle tasks. And you can do bad node or good node, and I'll put that in the README so that you'll see that. There are 3 to 5 nodes. We can actually add another node. I can actually. Okay, and you can see adding another node right here, and you'll see it pop up over here because node connected forward leader. So it's threaded as well, so it will continuously look for those nodes forever. And obviously, the thread will continue running, but I've set it to block at 5 nodes. So we've got that, and you can go up to 5 nodes, like I said. Let's go ahead and test if it's fewer than 3 nodes, what happens to the server. So controls. Let's go ahead and stop these. Let's run our client, or run our leader again. We'll run our client again. And let's just run 1 node. Let's run 1 good node. Actually, let's run 2 just for funsies. Okay. So, in fact, it'll still let you send this as long as the server is running. It doesn't matter how many nodes. The server will still accept requests from the client. But as you will see, if the client's is like 1, 2, 3, 4, 5, 6, and 7, with a delay of 100, whatever, you will see a failure request. It failed, and it says insufficient nodes available to complete request. You can keep going, and if you run another node, it'll work. And we'll do that in a second. So there's no fewer than 3 nodes. The leader should send an error message. The client input should ask the user for an input. We got that. There's single sum calculation. As you see, when we do get something running, so let's run another good node. Yes, we'd like that. Okay, so now we have 3 nodes. 1, 2. Oh, and I also want to show you, so like, just because we have 3 nodes, I was running into an issue. Well, not an issue, but just a semantic issue. I didn't want, so just like when we have some algorithms that take it down to the single, like the merge sort or something like that, where it goes down to 1 element. I wanted it to, if we had fewer than 1 or fewer than the nodes running, that when we sent a list that was smaller than that, that each one would go to the list, the smallest list would be a single individual number. So that's what I did. I sent where it would send each one a single individual number if there's enough for each, or it would send an empty list, and the empty list would just be returned, or the node would with 0 computational time, or if there was a single number, it would just return that single number with 0 computational time because it doesn't take any time to computate, because it's only between the positives. So like just 1, 2, and 3 with a delay of 100, we get that the sum was 6 as well. But you'll see the distributed and non-distributed times are a lot less than that, because I mean they still have the overhead obviously, but they don't compute like that. So I just wanted that to be put out there. But you do see the performance comparison right here. You also see the performance comparison. You don't. Yes, but you do see the performance comparison right here on the screen right here. You just saw how we were able to simulate faulty nodes by running bad node. The consensus check for verification, you were able to see that when we had a bad node and it sent back that the message failed because the node was because the checksum failure. Yeah, right here. So message computation failure, checksum failure. Just so that's there. The client displays results clearly. I feel like that's pretty clear. Maybe I could do more spaces in between things to make it a little bit better, but I do feel like I feel like it's pretty clear to me what's going on there. The testing, I'll write some test cases so that you will be able to like run those if you like, or I can just write them out if you want. But I know I probably can't go through everything, but I do have where you can say no, and it exits pretty gracefully. And over here, it talks about the client request closes. It does close the client request connections. I didn't really build an exit strategy for the nodes because I didn't feel like they should be exiting at all. I think they should just stay up. That would just be me. And I did have some for I do. There are obviously catches exceptions if the nodes just run offline. Um, but I feel like I did pretty good error handling on that. So let's just like run client again. It'll connect again. There we go. Protocol works. So if I did random numbers or whatever, it won't let you. It says that the list was not formatted correctly with integers. Say I did like 1, 2, 6 dot whatever. It won't let you there. It literally only lets you put integers that are parsed by like a comma. So 1, 2, 3, 4. It does let you, however, put a single integer in there with a delay time, but that is it does work obviously because it's just a single list. The non-distributed time is going to be really crazy small on that, obviously, because it literally doesn't even have to count. It just goes up. And then we have overhead, obviously, for the distributed time because it has to send it to a node and then respond to the node. You can see here where it did send it out and then those nodes received responses. And the checksum as well. Believe that's everything. Yep, I'll add some more print line so you'll probably if you run these again, you'll probably see a little bit more print line over in the nodes, just so you can kind of see what's going on under the hood. I feel like if this is too much, obviously you can go in and mark out what you don't like and run that code. But I enjoyed seeing exactly what was happening in that hub essentially. And I feel like this is pretty valuable because I feel like the user doesn't want to be bogged down with a bunch. There were a few things like the responses received and transmitted. I just thought those were useful just so you could see what was going on, especially from like a debugging kind of platform or way. But I did want to put that in there. So I didn't want to bog it down too much, but I also kind of wanted to see what was being sent and received. But that's it. That's my distributed network. You can look at that README for the rest of those commands or the full command line or that you can run, and my program's explanation, functionality, and stuff like that. And the screencast will also be in there, so I guess you would have seen that already. But I hope you guys have a good day. This was actually really super fun to make, and I'll see you later. Bye.